This diagram illustrates the full reach of a power system, connecting massive generating plants and high-voltage transmission lines to the final consumer. We interact with this infrastructure every day, but the energy itself, the actual movement of electrons within those cables, remains invisible. Controlling a system we cannot see requires a reliable mental model. Without a way to visualize the flow, these forces behave like an unpredictable vacuum. The hydraulic analogy provides that conceptual bridge, mapping electrical variables to the physical movement of water through pipes. By applying these plumbing mechanics to electricity, these invisible forces begin to follow a predictable logic of pressure and flow. Consider a closed loop of pipe filled with water. With no external force acting on it, the water remains perfectly static. Add a pump to the loop, and it builds pressure against the water, creating the potential for flow. In a circuit, this pressure is voltage, also known as electromotive force. It is the potential energy pushing electrons through a conductor. Voltage is the necessary first step. Without that initial push, no electrical work can be performed. When that pressure has an open path, the water responds by rushing through the loop. This movement is current. It is a measurement of the volume of electrical charge passing through a point in the circuit every second, measured in amperes. The result is proportional to the cause. If the pump increases the pressure, the volume of the flow increases with it. Current is the energy in motion, the physical manifestation of the push that actually reaches the connected device. This flow is never entirely unchecked. The physical diameter of the pipe and the friction of the interior walls naturally resist the movement. We map this to resistance, the property that opposes the flow of electrons and converts a portion of that energy into heat. This analysis shows resistance is a physical calculation. Equation 4.1 demonstrates its atomic function of the conductor's length and cross-sectional area. These values shift based on the environment. Equation 4.2 shows how a conductor's resistance climbs as temperature increases. This friction acts as a constant physical constraint, establishing the predictable boundaries within which any electrical circuit must operate. These variables are unified by Ohm's law. Voltage equals current multiplied by resistance. This relationship is proportional. If resistance is constant, doubling voltage doubles the current. The relationship is also inverse. If voltage is locked, increasing resistance forces the current to drop. These three forces are always in balance. Changing one variable triggers an immediate calculable reaction in the others. We can apply this synthesis to a simple physical loop: a battery, copper wires, and a lamp. The battery acts as the pump, providing voltage, while the copper wire serves as the path for the current. The lamp's filament is a high-resistance material. It uses the friction of flowing electrons to generate heat and light, effectively turning resistance into a tool. Maintaining the balance is critical. Too much resistance dims the bulb, but too much voltage forces a surge that can burn it out. Electrical power functions as a manageable mechanical system, defined by the relationship between the force that pushes, the volume that flows, and friction that limits them both.